welcome to today's class. Today we're going to be looking at something called Mohrs Stress Circle. Up until now we've been looking at complex stress and we've been using analytical techniques. So that is to say we've been using equations and we've been putting numbers into those equations, and we've been working out stresses, direct stresses and shear stresses on any plane of interest, and then principal stresses and principal planes, i.e. the maximum direct stress and the planes on which they act, or the maximum or minimum direct stresses. You can also use graphical methods. There was an engineer called Moore who realized that the equation that we come up with in the principal stress derivation is actually just the equation of a circle. So you can use Mohrs circle and you can work out direct stresses, shear stresses, principal stresses, and the planes on which they act using graphical techniques. So rather than using equations, we can be using graphical techniques. So that's what today's class is all about. I'm going to be showing you how to use Mohrs circle, how to construct it, how to read information off it, why it works. So we'll go through the proof to show that we're essentially using the same equations, or by reading stuff off the diagrams, we are essentially using the equations, and then we'll have a look at a couple of examples. Okay, so how does Mohrs circle work? I will put this PDF onto Teams and explains in a bit more detail about why it works, and there's a couple of derivations on there. We'll go through those in a minute, or a version of that which explains why it works. What's important to understand, if we scroll down, is this bit here, how we go about constructing Mohrs circle. And this is what I want to look at first. Okay, so we'll look at our question. We'll try to estimate what scale we need for each axis. That comes with experience once you've tried a couple of these. There are some questions actually at the end of this handout, and I'll upload some images, some GIFs related to those. So actually you don't need to do that. That's already been done for you. What you then do is plot sigma x and minus tor xy on the graph paper, and sigma y tor xy on the graph paper. Once you've plotted those 2 points, we join those together. That shows the diameter of the circle, and where that crosses the center line, that's going to be the center of our circle. We can then draw Mohrs circle and then read the relevant information from that. Okay, so creating it, we just follow these 6 steps. Okay, so we'll show in a bit more detail in a bit how we'd go about creating our circle, how we'd go about constructing it, and then how we'd go about answering the questions once we read information from Mohrs circle. Okay, what I want to do first is to show why it works. Okay, so here we've got Mohrs circle, which has already been constructed. So we've got a question, we've got an element subjected to 2-dimensional stress, and we've got our 2-dimensional stress system here. Okay, so on the x-axis we would plot direct stress, sigma. Okay, and on the y-axis we would plot shear stress, tor. Now, all that we need to remember is, to begin with, we're going to plot 2 points, and those 2 points anywhere on this circle, a point anywhere on this circle represents a plane on our 2-dimensional stress system. So if we think back to this sort of thing, our complex stress system, we've got a generalized case here. We've got an element subjected to direct stress in the x-axis and shear stress in the y-axis, and we've got a shear stress, positive shear stress, tor yx on this top plane, and the positive shear stress on the bottom plane. And because this thing's in equilibrium, we must have the shear stresses on those vertical planes as well. So there's our complex stress system. Okay, we could represent that by our Mohrs circle. So here would be our Mohrs circle representation of that. So any point on this circle represents a point on this element here. Okay, so we've plotted 2 points, tor sigma x tor xy minus tor xy, and sigma y tor xy. Okay, so sigma x tor xy, sigma x tor xy, let's say that's position E here, and sigma y minus tor xy, sigma y minus tor xy, that'd be position A. Okay, so we're going to plot those 2 points. Those 2 points represent positions on our plane. We draw a line through those. That's going to be the center of my circle. We can then construct our circle such that the center of the circle is at position C here, and then the circle goes through position A and through position E. Okay, so that's how we go about constructing our circle. So we've constructed our circle. We've got 2 points. Point E represents sigma x and minus tau xy. So if we look at our generalized 2D stress system, I've drawn it on there. Point E is the plane on which sigma x acts. Okay, so this plane here is represented by this point on the circle, point E. Okay, and in this plane here, the plane on which sigma y acts, we've got sigma y and tau yx. Sigma y, tau yx is position A. Okay, so plane A there is position A on my circle. Notice that on my circle, position A and position E, sorry, are 180 degrees apart from each other. They're on opposite sides of the circle. A and E are 180 degrees apart. But on my element here, A and E are 90 degrees apart. Okay, so we've got a factor of 2 there. Whenever we see 2 positions on my circle, if we calculate the distance, the angle between those 2 positions, that's going to be twice as big as the angle between the 2 planes on this, in our actual system. Okay, on our actual element. So whenever we calculate theta, it's actually 2 theta on my circle. So this would be 2 theta. So 2 theta is 180 degrees here. Theta would be 90 degrees here. We need to calculate the angle on the circle and halve it to work out what is the angle on our 2-dimensional stress system. So any position on this circle represents a plane on my 2-dimensional stress system. Okay, let's think about what else we've calculated. We've been talking about principal stresses, and principal stresses are maximum direct stresses. So this position here, shown by G, would be sigma 1, the maximum principal stress. And notice when the stress maximum, whether the principal stress is a maximum, the shear stress is 0, and that's what we've shown in the previous class. So at sigma 1, we've got a 0 shear stress. F here would be sigma 2, the minimum principal stress. Again, when we've got a principal stress, with our shear stress is 0. Okay, so G represents our maximum principal stress, F represents our minimum principal stress. If we wanted to calculate the maximum shear stress, well, that would be directly above position C here. Would be there, wouldn't it? That would be the maximum the maximum shear stress, and would be this location here. So we can just read that off my graph there. Okay, if we want to calculate the position of those things, we can see G and F are 180 degrees apart. In reality, on my element, they would be 90 degrees apart, which is again something that we've discussed in a previous class, that my maximum principal stress and my minimum principal stress are always 90 degrees apart. Okay, so looking at my circle, we can calculate the principal stresses, we can calculate the maximum shear stresses, we can calculate the positions of those planes relative to each other by measuring an angle off of my circle and then halving that angle. That's going to be the location of those things on my 2-dimensional stress system. Okay, so let's show why it works. Okay, so we've constructed Mohrs Circle. We've plotted position A and position E. So E, remember, was sigma x minus tau xy. So we've looked at our question and we've extracted sigma x and tau xy and plotted position E. We've also plotted position A, sigma y and tau xy. So we've looked at our question, we've extracted sigma y, we know what tau xy is, so therefore we can plot A. So we've got these 2 positions on my circle A and E. Remember, any plane within my stress system is a position on my circle. So we've just calculated 2 positions on the outside of that circle. So we can draw a line between them, and where that crosses the x-axis, that's going to be the center of my circle. We can then construct this circle. Okay, so we've got those points there. So position E, sigma x minus tau xy, and sigma position A is sigma y tau xy. Okay, so I've then put some other labels on my circle. I've got my origin here. There's A, B would be sigma y, C would be the center of my circle, D is sigma x, E we've plotted, F is our minimum principal plane, minimum principal stress, should I say, and G would be our maximum principal stress. So OB, distance between O and B, is sigma y. OD would be sigma x. DE, where's position D? DE would be minus tau xy, and BA would be tau yx. Okay, I've then used a little bit of trig to work out these other locations here. CD, whereas CD is this distance here. CD would be the difference between sigma x and sigma y, difference between sigma x and sigma y, and then half of that. So a half sigma x minus sigma y. OC from the origin to the center of the circle is the same as OD minus CD. Okay, OD minus CD. OD, remember, was sigma x, got that up here, and CD, we've just shown is a half sigma x minus sigma y, half sigma x minus sigma y. So you end up with, let me zoom in there a little bit, sigma x minus a half sigma x plus sigma y. So that's a half sigma x plus sigma y would be OC. So if we wanted to extract, I've just said to you that OG would be the maximum shears, maximum direct stress. Okay, so let's now show that that distance from O to G is in fact sigma 1. Is the same as using that big long equation that we came up with. If we cast our minds back to this handout here, we showed that sigma 1 was this big long equation here. Okay, so let's show that actually reading position G would be the same as using that equation. So we can use graphical techniques, these techniques here, instead of these analytical techniques, instead of using this formula. Okay, so sigma 1 equals OC, so the origin to the center of the circle, plus CG, plus the radius of the circle. So that's OC plus the radius of the circle, which is the same as OC plus CA. OC plus CA. So from the origin to the center of the circle, the distance from the origin to the center of the circle plus the radius of the circle. Clearly we can say that OC C plus CG is the same as OC plus CA. It's just the origin to the center of the circle plus the radius of the circle. Now, we've shown up here, OC was a half sigma x plus sigma y. So OC is a half sigma x plus sigma y. CA, the radius of my circle, we can use a little bit of trig, and we know that we've got a right angled triangle here. So that hypotenuse there squared is equal to this length squared plus this length squared. Okay, so CA squared, that's the hypotenuse, CA squared, i.e. the radius of the circle, CA squared equals BC squared, so this length here, BC squared, plus BA squared. BA squared is going to be this distance here. Okay, so we've just used a bit of Pythagoras there to work out the length of the radius of the circle, i.e. the hypotenuse of this triangle. So CA squared equals BC squared plus BA squared. So CA is the square root of that lot. BC squared, BC squared, BC squared is going to be the same as CD squared, CD squared. Okay, looking at our geometry here, looking at our situation, this length here, squared, is clearly going to be the same as this length here, squared. Okay, so BC squared is the same as CD squared. So I've just substituted that in there, CD squared plus BA squared. Now, CD, we've already calculated up here, look, was a half sigma x minus sigma y. So that's a half sigma x minus sigma y squared plus BA squared. BA squared, well, BA was tau xy. So we've got tau xy squared. So CA is the square root of that lot. That's what we've just shown there. We can take half squared out of that bracket, which is clearly a quarter. Sigma x minus sigma y squared plus tau xy squared. We can then factorize this. Why are we going to do that? Well, we've got a quarter times by this. We need to times this. If we're going to times that by a quarter as well, we need to multiply it by 4 to start with. So we've got a quarter times by that plus a quarter times by that. We've now times everything by a quarter. We take the square root of a quarter, that's a half. So we can take that outside our square root sign. So we've got a half sigma x minus sigma y squared plus 4 tau xy squared. Okay, that's CA. So why have we done that? Well, we've just calculated what CA is now. We've got that there. That's the radius of my circle, remember. And then OC, we calculated up here. OC was a half sigma x plus sigma y. So sigma 1 OC plus CA, so that's a half sigma x plus sigma y plus a half, and then that square root sign. So that's our maximum principal stress. Now, if we compare that equation to this equation here, it's the same. Here we've factorized it slightly differently. Here we've got a half times by that and then a half times by that. Here we've got half times by that and the half times by that. So sigma 1, we're adding those two things together. So it's the origin, distance to the origin plus the radius of the circle. And the minimum principal stress would be the distance to the origin minus the radius of the circle. We think back to Mohrs Circle, the origin of the circle to the center of the circle, sorry, the origin to the center of the circle plus the radius is going to give you sigma g, sigma 1. The origin to the center of the circle minus the radius of the circle is going to give you sigma 2, position F. Okay, so we can use Mohrs Circle and we can extract that information. Okay, and hopefully you can see there that by reading information from my circle is exactly the same as using these equations here. Okay, we've shown that is true for sigma 1 and sigma 2. You can also show that for the maximum shear stress and so on. Okay, so let's now have a look at those. Let's actually use Mohrs Circle using those 6 steps that we've talked about to construct a Mohrs Circle. We can then read information from that, and we know reading information from that circle, which is shown here. For example, sigma 1, this position here, is exactly the same as using that equation there. It's the origin of the circle to the center of the circle plus the radius of the circle. And sigma 2, if we were to read sigma 2 from that diagram, position F, that's exactly the same as using this information here. It's the distance from the origin to the center of the circle minus the radius of the circle. Okay, so let's now try and construct a Mohrs Circle and have a go at some of those questions. So I'll upload this PDF, which explains about Mohrs Circle, and we've got those 6 steps for constructing Mohrs Circle, and we'll see at the end of that handout we have some questions. There are 3 questions at the end of that. And actually, we'll see some of those questions are the same as the questions that we saw in this handout, the complex stress handout. So if we have a look at the question number 1, so here's our Mohrs Circle handout. Question number 1, we've got under certain loading conditions, the stresses in the wall of a cylinder are as follows, 80 and 30, and so on. Okay, if we look at our complex stress handout, which was this one, and we have a look at question in there. Question number 1, under certain loading conditions, the walls and the stresses in the walls of a cylinder are as follows, 80 and 30. Okay, so previously we've answered that question using equations. So we've used that equation there, for example, to work out what our principal stresses are. And we've done that in this question here. What I'm saying now is we can actually answer exactly the same question using Mohrs Circle. Obviously, it's not going to be as accurate as using equations because we're reading information from graphs and so on, but we can work out what the principal stresses are and the planes on which they act. So at the end of the Mohrs Circle handout, we've got 3 questions. Question 1 has 2 parts to it. We've got this loading condition is part A, and then part B says on these results, if owing to a change of loading, A becomes compressive whilst B and C remain unchanged. So there's 2 parts to question 1, part A and B. And then we've got question 2 and we've got question 3. What I'll do, I'll upload images associated with those questions. Question 1A, 1B, 2 and 3. Okay, so those, if we open this in Word Paint, or sorry, Paint 3D, there's Paint 3D, there we go. So if we look at this question here, there's our situation, and you can see on there what I've drawn is the x-axis, which is the direct stress, remember, and the y-axis, which is the shear stress. So we're going to use this piece of graph paper here, this image, to create Mohrs Circle, and then from Mohrs Circle we can extract the information needed to answer that question. So let's do that. Let's answer question number 1. So there's question number 1. Under certain loading conditions, the stresses in all of a cylinder are as follows: 80 megapascals in tension. Okay, now I'm going to assume that that is direct stress in the x direction, 80 megapascals in tension. Okay, so let me draw that. If we draw our element, there's our element, and we have assumed that we've got a direct stress in this direction of 80 megapascals. Okay, I'll draw all of my stresses in megapascals. So we've got 80 megapascals in that direction. We've got 80 megapascals in that direction. And 30 megapascals tensile right angles to A. Now I've assumed there that's 30 megapascals in Y. Okay, so let's draw that in the Y direction. We would have 30 megapascals in that direction. Okay, again, I'm assuming those are megapascals. All my stresses are in megapascals. So I've got 30 megapascals in that direction. Shear stresses of 60 megapascals on the planes on which the stresses A and B act. The couple acting on the planes carrying the 30 megapascal stress is clockwise in effect. Okay, so if I draw those on the 30 megapascal plane clockwise, trying to rotate my element clockwise, they're going to be going in that direction, aren't they? Okay, so I've got 30 megapascals in that direction. 60 megapascals in that direction. And 60 megapascals in that direction. And then if this thing is set in equilibrium, there must be equal and opposite shear stresses on this plane. And there must be equal and opposite shear stresses acting in the opposite direction, acting on this plane. Okay, and I won't label those. So that 60 refers to that vector and that vector, and that 60 refers to that vector and that vector. Okay, so there's our situation. You zoom out a little bit. Question number one, we've got our direct stress of 80 megapascals shown in the x direction, our direct stress of 30 megapascals shown in the y direction, and our 60 megapascal stress, our shear stress is clockwise in effect. And what that means is on the top surface, if we're going from left to right, that's a positive shear stress, 60 megapascals. Okay, so we've interpreted our question, we've extracted that information. What we can do now is we can construct a Mohrs circle, and you'll see in these images in the top left hand corner there, I've put those 6 steps there for you. Okay, so looking at your question, try to estimate what scale you need for each axis, plot the x-axis, which is the direct stress, and the y-axis, which is plus or minus the shear stress. Okay, so I've already done that. Okay, so we're going to now look at part 2. Step 2, plot sigma x minus tau xy on your graph paper. Okay, so let's plot those points. So the first point we're going to plot is sigma x minus tau xy. Sigma x is 80, so that's 80 in the x-axis, and minus tau xy, so that's going to be minus 30. So 80 minus 30. So if we zoom in here, 80 minus 60, isn't it? It's sigma x and minus tau xy. Tau xy is 60, so minus tau xy would be minus 60, so it's 80 minus 60. So let's zoom in here, 80 along 2, 4, 6, 80, and then 60 down 2, 4, 60. It's going to be this position here. Okay, so we're going to plot that point there. Let's just zoom out a little bit. So that is sigma x, and a minus tau xy minus tau xy. It's going to be that point there. And then the next point that we need to plot, looking up here, is going to be sigma y. So this is step number 3 now. Plot on your graph paper, sigma y tau xy. So sigma y is 30. So it's going to be 30, 60. So we're going to plot on our graph paper 30 along and 60 up. We've got 2, 4, 6, 8, 10, 2, 3. Okay, so each one is 2. So 30 will be 20, 22, 24, 26, 28, 30, and 60. So if we just zoom in here, 60 is going to be that line there, and 20, 2, 4, 6, 8, 10. It's going to be there, isn't it? Going to be that position there. It's going to be 30, 60. Okay, and that is sigma y and tau xy. So that's our 2 points plotted. That's going to form 2 points on our circle. What we need to do now is draw a straight line between those 2 points. That's going to tell us where the center of the circle is, and then we can construct Mohrs circle. So let's do that. 2D shapes, draw our line. We're going to draw a line between, just zoom in a little bit, draw a line between there. No, something like that. Draw a line between there and there. Let's do that a bit more accurately. Draw a line between. So the answers we get are obviously going to be as accurate as we are here. So let's try and do this nice and accurately. We're going to draw a line between there and there. Okay, that's going to show me the radius of my circle. Sorry, the diameter of my circle. What we're going to do now is draw my circle using that information. So we look at our steps. We've plotted our 2 points. We've joined points 1 and 2 together. This shows the diameter of the circle. So that's that line now I've just drawn, and the center of the circle where the line crosses the x-axis. So that's going to be that position there. Draw Mohrs circle. Okay. So using that information now, we can draw Mohrs circle. So let's do that. So we'll click on our 2D shapes, go to our circle, we'll hold down Shift and Control, center of our circle there, and then Mohrs circle goes through those 2 points that we've just created there. So we'll extract that until it goes through those 2 points, which is about there. And we've got Mohrs circle. So what we can do now is we can extract information from that to answer the question. Draw a small circle, read the relevant information. So let's look back to the question. What does the question actually ask us? It's this one here, isn't it? Okay, let's have a look at our question. Calculate the principal stresses and the planes on which they act. Okay, the principal stresses. So what is sigma 1 and what is sigma 2? So sigma 1, our maximum principal stress, remember, is going to be the maximum direct stress. Now looking at our circle, our maximum direct stress is going to be here, and that is 100 and 2, 4, 6, 8, 10, 110, 12, 14, 16, 18, about 119 megapascals. Okay, and if we look at our answer, it says there 120 megapascals. Okay, close. So clearly I'm not doing that 100% accurately, but we've got 120 megapascals. And so that's the maximum principal stress. Now the minimum principal stress, if we look back at our circle, our minimum principal stress is going to be this location here, where it crosses the x-axis. Okay, and we've got, there's our origin, -2, 4, 6, 8, 10, about -11.5 megapascals, -12 megapascals, something like that. Again, let's have a look at our answer, -10 megapascals. Okay, so you can see we're not 100% accurate, but we're close. We've got -10 megapascals, and the planes on which they act. So let's calculate the position where we would find those principal stresses. Okay, so our maximum principal stress is here. We want to know what is the location of that relative to either plane BC or plane AB. Okay, now we can extract that information from our graph. Now remember, an angle on our graph or on our graph paper would be 2 theta relative to theta on our real system. So let's draw our square. If we hold down Control, we should be able to draw that. There you go. So you can see I'm drawing my square, but I'm just going to draw it as a line. So a square with 0 length on the sides. Now the reason I'm going to do that is so that I can then rotate it. And as I rotate it, I mean, you can see that it's showing me the angle. So the angle between this position BC to this position here, my maximum principal stress, you can see is 67 degrees. Okay, 67 degrees. If we go from 67 degrees anti-clockwise from plane BC, we will get to this position here where my principal stresses occur. Okay, 67 degrees. Now, if we have a look at the answer is actually 33.5 degrees. Okay, so we need to take that angle and halve it. Okay, so that angle here was 67 degrees. So the actual answer would be 33.5 degrees. Okay, so from plane BC, we would go 33.5 degrees in an anti-clockwise way to get the maximum principal stress. Okay, so from plane BC, there's plane BC, and this vertical plane, we would go 33.5 degrees anti-clockwise to the plane where our principal stress occurs. So I can actually draw that plane. So if I were to draw a line down here, for example, let's colour that orange. Does that work? No, it doesn't. Okay. Let's I'll draw over the top of that. Okay, so that orange line there, that angle between plane BC, which is the vertical plane, 33.5 degrees in an anti-clockwise direction, I would get to this plane here. That is where my principal stresses occur. Okay, so the principal stresses, the direct stresses at that location there would actually be a maximum. We'd call that sigma 1, and that would be 120 megapascals. So 120 megapascals on that plane there, acting away from that plane because it's a positive value, and the angle between that vertical plane and that plane there that I've just drawn, 33.5 degrees. Okay, so we've calculated the location of sigma 1 relative to plane BC. What we need to do now is calculate the position of sigma 2. Okay, now relative to plane BC, that's going to be a further 180 degrees. So remember, this was 67 degrees, and if we add 180 degrees onto that, that would be 247 degrees. Okay, now remember, this is 2 times theta in our element. Okay, so 247 degrees divided by 2 is going to tell us the location of the minimum principal stress relative to plane BC when traveling in this direction. So traveling in an anti-clockwise direction, we're going to go that angle to get from that plane there, plane BC, to this plane here where our minimum principal stress occurs. Okay, so 67 plus 180, so that's going to be 247. If we do 247 divided by 2, that's going to give me 123.5 degrees. Okay, so let's have a look at our answer, wherever that is. 123.5 degrees. Yeah, 123.5 degrees. So that's where that comes from. So that's going to tell me the position of that minimum principal stress when measured in an anti-clockwise direction from the location of our plane that we've drawn. So plane BC, we're going to move in that distance there. So notice the maximum principal stress and the minimum principal stress on our circle are always going to be 180 degrees apart from each other because they're on the opposite sides of the circle, just like in reality on our element, they're always 90 degrees apart from each other. Okay, so that's how we would extract that information. What we can also extract from this circle, the question doesn't actually ask us, is what is the maximum principal stress? So our maximum principal stress would be about, what's that, 66 megapascals, something like that. Yeah, about 66 megapascals. And we can see where that occurs. That occurs just there, look, on that plane there. We could extract that information if we wanted to. Okay, so that's Mohrs Circle. That's how we go about constructing it. That's how we go about extracting information from Mohrs Circle. What I'm going to do, I'm going to upload various PDFs. So there's this PDF here, which we've gone through, which has some derivations, which I've gone through in a bit more detail, actually, and the basic steps that we go through. And then there are some questions on there. I'll also upload this PDF. This PDF shows me going through that information. I'm going through those questions. You can see I've drawn it out on a piece of graph paper. So I would recommend you do the same thing. Get yourself a bit of graph paper and a compass and a protractor, and actually try constructing that stuff and see how you would get that information from those questions. And I will also upload these GIF files, GIF file for question 1A, 1B, 2 and 3. So if you want, you can try those in Paint 3D in the same way that I have in this video. So hopefully what you can get from all of that information is using graphical techniques, using Mohrs Circle in order to understand complex stress. As always, if you've got any questions regarding any of this, let me know in class or drop me an email, and I can hopefully help you. Until next time, okay, cheers, bye-bye.